Is it going? Yes, it is. Hi, everyone. Thanks for showing up for your learning today. It's great to see you all. I'm glad that we get to meet in person to do these types of lessons together. This is our last new topic for this unit, Unit 3, and it talks about working the opposite way that we normally do, where we're now going to take a collection of data points and try and model those data points with a quadratic equation. One moment, let me boop the thing. This one, and we'll get going. So taking a data set and then modeling that with a quadratic equation, what that can allow you to do is if the data is indeed quadratic, then it can allow you to predict the future or even have some insight into what might have happened in the past. So let's take a look at some ways that we might do that. One example might be in a volleyball game. With these types of word questions, always start by drawing a picture. Candace, she serves a ball underhand. So I would suggest draw a little picture of Candace. We'll say Candace is a fighting owl, so we'll draw her an orange. Here she is here. Okay, so that's my expert stick figure. She's serving the ball from that point. It's 2 feet above the floor where she hits it. The little single apostrophe, that's a foot. So it's 2 feet. That looks to me like about 2 feet. Maybe she's not too tall. She serves it underhand. It's 2 feet. So this is 2 feet high. There, 2 feet. And it's from the edge of the court. So this is the beginning of the court where she hits it from. A volleyball court is, well, if the net is 30 feet away, we better put the net on. It's 8 feet tall. So here we'll call this the net, 8 feet. And that's at 30 feet away. And so the whole court, a volleyball court, is 60 feet long. So there we go. And now we know that her volleyball goes to a maximum height of 14 and a half feet, 25 feet away. So that would be like this up here. We'd have that point up there at 14 point, the point 25 away, 14.5 in the air. And we want to know, is this ball going to go up here, go through that point, come down and land in the court or not? Okay. So now we've got a picture. The picture is going to guide our understanding of this question and what we're seeing here and help us answer this question. So the first thing that we're going to need to do is, if we want to use quadratics and the quadratic formula to analyze this, well, first of all, make a guess. Is this ball going to be in, or is it going to hit the net, or is it going to be too far and it's going to be out based on this quadratic? Let's draw it a little more beautifully. We'll use Desmos to draw it more beautifully. I go in Desmos, and this is how you put a table into Desmos. This is useful if you want to do a more complex example, and you can even use this to analyze some of your textbook questions. I know it's hit from an x value of 0 and a y value of 2. I know that an x value of 25, it's 14.5 high. And then I zoom out so I can see those 2 points. I can also put the net in there. Maybe I'll use the line x equals 30 for the net, but I want to only draw that 8 feet high. So 8 is greater than y. And the squiggle bracket. There we go. This should be a squiggle bracket here. There. So that's the net. At its highest, it's 8 feet high, and the court goes all the way to 60. So now you can see this thing. If I draw a quadratic through those 2 points, where that's the vertex, do you predict that it would be in or out? Y'all played volleyball when you were in junior high or in grade 9 phys ed. Is that going to be in or out? If I serve it from here, it goes up, reaches its maximum height, if it comes down again. Is that going to be in or out? What is your prediction? I kind of predict in. I think it's going to be in. Now, how do we use math to analyze this? Let's take a look. First step, and this actually is a skill that we had in Unit 1. It was a skill that we want to practice again from Unit 1 because we weren't particularly strong at it then. This is using the vertex form of a quadratic to create an equation. So I know that if I had a vertex form equation, this point here, 25, 14.5 is the vertex. So this equation looks something like this. Y is equal to, I don't know the stretch factor yet, call it A. X minus h squared plus k. This is the general vertex form equation. Then I go ahead and put in 25, 14.5 for h and k. So I'll have this equation. Y is equal to a multiplied by x minus 25 squared plus 14.5. So that's taking the coordinates of the vertex there, 25, 14 and a half. We were told it was this high, this far away. So that's the x value of the vertex. That's the y value of the vertex. And then I just input it. Now I know one other point, and that's this point over here. I need one more point to solve for that a value, to solve for that stretch factor. And that's the point 0, 2. So let's put that point in to the equation to solve for a. When y is equal to 2, x is equal to 0. So 2 is equal to a multiplied by 0 minus 25 squared plus 14.5. Okay? Now, I'm wishing I drew my picture a little smaller, but here we go. 0 minus 25 is just negative 25. So I'm going to actually bring this, I'm going to do it this way. I'm going to bring this up here and keep going. So this is 2 is equal to a multiplied by 0 minus 25 squared plus 14.5. So 0 minus 25, that's just negative 25. So let's just call it that. And then I'm going to try and isolate a. I want to get a alone and solve for it. So let's take away this 14 and a half and move it to the other side. And that will give us another line, which looks like this. Negative 12.5 to minus 14.5 is negative 12.5 is equal to a multiplied by negative 25 squared. Negative 25 squared, your calculator will tell you that that's 625 multiplied by a. So by moving this away, that's now 0. So that's gone. We had this giving us that. And then minus 25 squared is 625. So all I'm doing is all the simplification that I possibly can in order to find out a. I now notice that I'm multiplying a by 625. I don't want to do that, so I divide it by 625. Negative 12.5 divided by 625, that actually reduces to, I believe it's, is that 1 over 50? Anyway, let's see. You can get a decimal here, 12.5, but it's negative. Divide by 625 is equal to negative 0.02. It's negative 1 over 50, like I said. So here we go. This is just evaluate. Negative 0.02 is equal to a. All right. Now we have the equation of this quadratic. It is equal to, we had everything we wanted in the quadratic there, except for a. So we can write that out again. Let's use purple because we're triumphantly writing down our equation. Y is equal to negative 0.02 multiplied by x minus 25 squared plus 14.5. That's the equation of this quadratic. Let's go ahead and throw that into Desmos, and we'll do some analyzing of it. Y is equal to negative 0.02 multiplied by x minus 25 and the bracket squared plus 14.5. Notice that it goes through these points, it bullseyes them just perfectly because our algebra is good, and it predicts that the ball will land after 51.9 feet and go over the net. So Desmos is suggesting that this is going to go in and be a good shot. Now, how would we do that if we wanted to, if we didn't have access to Desmos? Well, I want to know first of all, what's its height as it goes over the net, which is at 30 feet, and we want to be at least 8 feet high at 30. What I would do is input 30 here. I would say this is equal to negative 0.02 multiplied by 30 minus 25 and the bracket squared plus 14.5. And if I evaluate that, I'm told that that's 14. How is that 14? Well, work it out. 30 minus 25, work it out with your bedness. Hey, Lauren, can you see this back there? It's big enough? Okay. 30 minus 25 is 5. 5 squared is 25. 25 times negative 0.02, work it out on your calculator. Where is it, calculator? 0.02, but it's negative, multiplied by 25 equals negative a half. Okay? So that part there is all negative a half. Negative a half plus 14 and a half is just 14. So when we check over here, let me erase my this. This is giving us a value of 14 feet in the air as it goes over the net. 30, 14 right there. So it's certainly over the net. Now we need to check what's the value of that root. Is the value of that root going to be greater than 60, meaning it's outside the court, or less than 60, meaning it's inside the court? And so we can work that out using the quadratic formula and a lot more paper. So in order to do that, I would need to use quadratic formula on this equation. Notice that that's not yet a quadratic in standard form. You'll need to expand that to standard form and then apply the quadratic formula, find the value of the roots, and find that one of them is indeed in the net. Okay? And this is why I wanted to have a meeting about what do you want to see on the test or not. Yeah. Let's keep going. Let's actually take a look at my example 3 on the back side of the page. Let's say we were taking a look at test scores given how long people have studied. We could suggest that this might be quadratic in that if you don't study very much, your mark might be low. If you study the right amount, the sweet spot, you'll maximize your mark. And if you study for too long, you'll be too tired, you'll hate the stuff, and you won't get very good. So your mark goes up until it reaches the sweet spot, and then it goes down. Let's find the sweet spot, and we'll see if we can model people's test marks with an equation. To do these types of problems, go ahead and throw your points onto the graph. So 0, 20%. That's I study 0 hours and I get 20% on the test. That's about there. 1, 60%. Oh, that's not bad. If I even study just for an hour, I'll do pretty well. That's up there. 2, 83%. A little bit more studying paid off. We get about up there. 3 hours, 90%. Oh, cool. That's pretty good. That's up there. 3.5 hours. So 3.5 would be up about that high. 88%. It's only come down a little bit. And 4.5 hours, 73%. Okay, so 73%, it's over there. 4.5 hours in between 5 and 4. It's about there. All right. So if you want to model a data set like this with a graph, the way you do it is you take your table, plot them, and then sketch the quadratic that goes through those points. And it might look something like that. Okay. Maybe something like this. This is fairly rough. Using a piece of graph paper will give you better results, but if you want back of the cocktail napkin, this is fine. And then, once you're done plotting, you say, well, I'm going to guess what the vertex is. Just guess. In this case, it really looks like this point 390 is the vertex. This point here, 390. All right? So we guess it. It's 3 in the x, 90 in the y. If you study for about 3 hours, you might get about a 90. And you probably can't do much better than that. If you start studying more, you might tire yourself out and get a lower mark. Could happen. So If that's the vertex, then this is some kind of quadratic that looks like this. Y is equal to, I don't know the stretch factor yet, x minus 3 squared plus 90 will equal y. Then take some other point. We could take that point there. Sure. Let's use this point here, to find what our a value is. So then our next step is, after we guess the vertex, we're going to use one of the other points to find the equation of this graph. So in this case, when y is equal to 20, x was equal to 0. So we can put in 20 for x is equal to a multiplied by 0 for x and 20 for y, 0 minus 3 squared plus 90. Okay? And now we do the same types of inverse operations to solve for the stretch factor that we were doing back in Unit 1. You're going to subtract 90 from both sides and resolve that bracket. So that's going to be negative 70 is equal to some number a multiplied by negative 3 squared. And then this went down to 0 anyway here, so that's all gone. So negative 3 squared is 9. So you would have negative 70 is equal to a multiplied by 9. And then you would divide both sides by 9 to find a. Negative 70 over 9 is equal to a. So then you would say, therefore, y is equal to negative 70 over 9 multiplied by x minus 3 squared plus 90 is the equation that can predict what mark you would get on the test if you studied X hours. Now let's take a look at how you would use Desmos to do this work for you and save you lots of time with the textbook type problems that I'm going to ask you to practice today. And then after you've had some practice today, you can decide if you want to have this skill on your test or not. Let's take a look. So I'm just going to set this up so that I can see my table and Desmos at the same time. So let's do this. And then we're just going to move this over a little bit. There we go. All right. So let's get a fresh Desmos here. Just going to clear all that stuff out. We're going to change our scale so that we can see y values up to 100%. We don't need to see negative 64%. That doesn't really exist, but showing us negative 10 means we can see the axis. And then we want to know how many hours do we need to study. Ain't no one studying negative hours. That's not possible. Let's just leave in negative 5 so we see something there. And then for the positive values, let's look at up to 10 hours of studying. Okay, there we go. Now, what you will do to model with a table, it goes like this. And you might want to bookmark this in the video if you're going to do this in the future to model something in physics classes or to find the equation that goes through a complex data set. This is how you would do it if you believe your data is quadratic. You go in here and you say add a table. This is the button to add a table. It allows you to enter x and y values. So I copy my table, 0, 20. And you'll notice it plots the points for me. I can see them as we're plotting. 0, 20, and then we keep going. 160, 1.5, 73, 2, 83, 3, 90, and we thought that looked like the vertex. 3.5, someone studied 3.5 hours and got an 88. And then someone studied 4.5 hours and got 73. Okay, so that might be our measured data. We measured this many students who studied a variety of different hours and got these different scores on the test. And then if we want Desmos to create an equation for that, this is what you do. This is a table of values, and it's called this table of values y1s and x1s. Okay, and we want to have a relationship between y1. You just write y1, and it immediately puts the 1 as a subscript there. y1 is approximately equal to, use the tilde here. Tilde is shift backwards apostrophe. It's up usually in the upper left-hand corner of your keyboard. A multiplied by bracket a x1, but it's x1 squared, plus b x1 plus C. Now what Desmos is doing is it sees that I want to know what's the relationship between my y1 values and my x1 values if I believe that I'm seeing x changing y quadratically. So I use the standard form here, ax1 squared plus bx1 plus c. That's my any quadratic can be that. And then it tells me here the R2, the R squared there tells me how reliably does this parabola predict the data. And the closer that number is to 1, the more accurate this parabola is. Right now it's extremely, extremely accurate. This parabola, you'll notice, bullseyes all those points. It's very, very close to a perfect model. The A value here is negative 7.8. We found that our A value was, where is it here? Negative 70 over 9. Let's compare negative 70 over 9 to what they have. 70, but it's negative, divided by 9 equals negative 7.7 repeating. Okay, we have here negative 7.8, so extremely close. And the B value is 46, meaning that that first hour of studying that you do gives you about a 40% jump or 46% jump. It's pretty accurate. We went from 0 hour studying to 1 hour studying, and we had a 40% jump. So that's pretty good. And then C at 20, the C at 20 just tells us the y-intercept. If we wanted it to output a vertex form parabola, no problem. You would just put in your general vertex form here. Bracket x minus h, end bracket, and then square it. Oh, but I need to have x1. Notice that it couldn't do it before I had x1 there, plus k. And now it outputs these values. It tells me my h is 2.99 and my k is 90.4. We had an h of negative 3, or well, 3, and they had an h of 2.9, extremely close. And then a value of plus 90 there. This is a value of 90.4. So extremely, extremely close. So doing it back of a cocktail napkin and just guessing the vertex got us extremely close to what Desmos is telling us is the absolute best quadratic approximation for this data table that we could possibly have. This is the way you model things with quadratics in Desmos. It's a very useful skill. It's an important skill to have to be able to do that. And I don't see how I can get that skill really onto the test for you, because it would be a Desmos thing. So any questions about this skill, you can hit me up. Practice problems, you can hit me up by email. Practice problems for this, you're going to find them. I'll show you in here. Boop, 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 boop. Here is our class. I will need to log in. No, I don't. Here is our unit outline. I only recommend 3 practice problems today, and I would recommend using Desmos to work with them in the way I showed you. They're down here at page 170, number 3, number 9, number 10. So I'll freeze the screen on there. Other things to note is this is our week this week. We're here November 8th, modeling with quadratic equations. Tomorrow we'll look at a practice test. November 10th will be a Delta Math and computer day to practice. And then November 11th will be the unit test. So let's chat about what we'd like to see on that unit test. Bye for now, everyone.